do it for now. Okay. Okay, why are we doing this? A lot of times it'll be workplace characterization, decide whether there's a hazard, whether the workers are exposed to higher than permissible exposure limit for any particular material that might be in the air. OSHA, you might be investigating employee complaints and applying to OSHA issues. You might be testing the effectiveness of anybody take industrial ventilation yet in this class, right? So you might be testing the effectiveness of whatever solution you've put together to control dust that's getting into the workplace using hoods or other devices. And you might be required, depending on what kind of material it might be that's in the air, you might have to be required to maintain a history or a log of worker exposures. Okay, so sampling methods, you want to inventory the chemicals, decide what the exposure is, so you know what procedure to use. You want to figure out what the work process is, so you know when the significant exposures take place. You want to know how long the exposures are, and you want to know what employees, you want to identify the employees that might be exposed. Okay, so let's take a look at the kind of devices that we're going to use. One situation might be that we are sampling an area rather than a specific worker. We might want to have a rough idea whether in this general area, what the levels of these particulates might be. For this week, we're talking about particulates. On other occasions, we might want to work with direct worker exposures. We might actually want to know exactly what kind of exposure a particular worker or group of workers has. Personal monitors are preferred. Number one, OSHA, for their evaluations for safety in the workplace, they require the worker be monitored, not they might not be satisfied with area monitoring. Okay, so for the most part, often worker exposures are measured over an 8-hour workplace exposure, over an average of an 8-hour workplace day. Okay, but in many instances, that may not be practical for a number of reasons. We're going to talk about that when we look at the NIOSH procedure for nuisance dust, for instance. We got to determine what kind of material it is. Is it a dust, a fume, a mist? Is it gas, vapor, so on and so forth? And how are we going to actually collect this material? Later on in the semester, we're going to talk about delivery of instruments. We're going to talk about detector tubes. We're going to talk about diffusion bags. But for now, we're going to look at a media type device for collection of a sample. Okay, so personal monitoring advantages over area monitors. You actually know what the worker's actual exposure is. Okay, so there are, OSHA and NIOSH have published guidelines or procedures for many exposures for many different kinds of industrial materials. NIOSH, for instance, there are procedures for measuring how much lead is in the air, how much asbestos is in the air, how much benzene is in the air. We're going to look at something simpler tonight. There's a whole classification of dusts that are not otherwise characterized. In other words, there's no specific procedure for them based on their toxicity. Okay, and that's very frequently called nuisance dust. OSHA and I actually call it other dusts that are not characterized, uncharacterized dusts. Okay, now the procedure for that is NIOSH 500. And we're going to take a look at that. A lot of health effects exposed that are associated with exposure to particulate material, lung cancer, COPD, so on and so forth. And we'll go through some of these as we get later on in the semester. We'll actually talk a bit more about this stuff. Tonight, we're just going to concentrate on actually taking some, assembling this and getting our first look at a sample train. A lot of health effects, particulate size particularly matters, cardiovascular effects. Now, in order to sample a worker's exposure, our primary concern is his breathing zone, the area where he's actually getting his air. So the way that we're going to do that is we're going to typically be concentrating on an area that's roughly the size of maybe 2 feet in diameter or so around his head. Okay, and so in order to do that, the device that we're using as a sampler has to be up close to his breathing zone. A lot of times It'll be a device connected to his collar, for instance. So the sampling device is actually in his breathing zone. The pump that we're using to draw air continuously is typically going to be portable. It's going to be mounted on his belt. These pumps can be, may just be that you start them and they start running. They may be programmable so that there's a delay before they start running. They run for a certain period of time and then shut off, and so on and so forth. Depending on what his work activities are and what the nature of the exposure is, you may be monitoring continuously over a whole 8-hour period. You may have this device running so that you either manually or automatically only sample during certain periods of time. Okay, so we have a pump, we have a sampling device, which is a filter, and some device to hold that filter in place. It also says size separator on there. Okay, now, if we have just a filter on there, well, that filter is going to capture whatever's in the air. So typically, that's going to capture total dust or total particulates that are in that worker's breathing zone. A lot of times we might not be interested in that. A lot of times we might be interested in particles within a certain size range. So in order to do that, in addition to that sampling device, we have something that we have to put in front of it that's going to make sure that the only things that get caught on that filter are particles that are in the range that we're interested in. Okay, that's that separator. And so what do these things look like? Well, these are typical filter cassettes. I'm going to throw a bunch out here. Okay. Okay. We'll pass these down. Take two to split up in groups of twos. Okay. And okay, I don't know how many I got down there. This should be enough for two to a group. If you get stuck, if there's one person alone or there's 3 people in a group, that's okay too. Okay, let me get one of those things. Let me borrow yours. Okay, now what I'm going to do is I'm going to open this device. How many of you have seen these before? Okay, good. At work? Okay. Yeah, I'm going to open this one. Now, you can borrow my knife. I'm not responsible if you cut yourself. Okay, these are sealed up. These particular ones are pre-weighed, and they have a serial number on them. Now, there's 2 ways that they do this. Most of the time, they're just pre-weighed. The laboratory gives them to you pre-weighed, gives you the serial number. You expose it, give it back to the laboratory with the number of liters of air that was pulled through here, and they will tell you what the increase in weight on the filter was. Okay, that's what that serial number does for you. Others of these are such that they are matched. There are 2 of them that are almost exactly, laboratory is screened, and they're almost precisely the same weight, the 2 filters. You expose one of the filters, the other one is a blank, and you send both back. You don't expose one, you expose the other, and they find the differences in the 2 of them. So there's 2 ways that you might get filters like this from the laboratory. Most of the time, though, you'll just simply get your own and expose them. So I'm going to cut this open, and I think I have at least 2 knives of some kind that you can use. Let's get this open. Okay. So, just so you know, typically most people, there's no hard rule here. Most hygienists put the blue little tab on the inlet side and the red one on the outlet side. So the air is going this direction, right? Okay, so inside this cassette, one part of the cassette slides into the other part of the cassette. It's smaller. And inside of the cassette, it traps a filter. There's a filter that's in that white pad is a filter. So I'm going to get rid of that filter, get the filter out of there. This filter actually has 2 parts. And these probably have been kind of squeezed together since the year of the flood, so it might not be that easy to get them apart, but I'll try. Okay, so here. So this filter really has 2 parts. One part is a 5-micron PVC filter. Okay. Normally you'd handle this with gloves and with tweezers and stuff like that. You wouldn't use your hands. That's a 5 micron PVC filter. It weighs almost nothing, right? Very, very light, right? Why PVC? This is the part that we're going to capture the dust on, and we're going to weigh before and weigh after we expose it to the air. Why do you think we might use PVC? Why wouldn't I use, say, something like cotton or cellulose, paper, cellulose? Why wouldn't I use one of those? What might I pick up? What might account for an increase in weight on a fiber like cotton or cellulose that might not be the dust that you pick up in the air? Moisture, right? So PVC filter, you don't have to worry as much about it absorbing moisture. So that's why one of the reasons why I use PVC filters for this particular application. Now, it's PVC filters, they tend to get a lot staticky and so on and so forth. That's not so bad for collecting dust because you want it to capture the dust. A little annoying when you handle them. Very frequently, there'll be a small like radioactive sort of little beta source next to a scale, next to the scale you would use. If you rub it across it, it takes the static away. So a lot of times you see a little pad next to your scale. I'm going to show you a picture of the scale in a moment. So we have this filter. The filter is very, very thin and very light. Now you're going to pull air through this, quite a bit of air through it. You're going to pull it through relatively, not that slowly, not fast, kind of at a medium speed. So the problem is that you could damage this filter as you're pulling air through it. So in order to keep it from getting damaged, you have another cotton filter, which is a backing. This is pretty rigid. You'll see this is pretty thick. Why is that there? That's just there as a backing, as a support for this filter. So first important thing, you got to make sure that the part you have that's in the path of the air, but first in the path of the air is the filter, not the backing. Don't reverse them. Okay, I can tell you there's a million horror stories of people, assembling their cassettes and taking 2 days worth of samples and so on and so forth, and then discovering that they ran them backwards. Right, it happens all the time. So you want to make sure you assemble it correctly. So I'm going to put it in. What's that?
You're saying assemble it. I mean, I didn't know you're assembling them. I thought you just get the cassette and
you can get it from a laboratory. You're actually going to assemble it. You're going to take the one that's in there out, and you have nice new backings and nice new PVC filters. So take them apart, play with the filter that you have in there, and then reassemble it with a new backing and filter. Okay?
I kind of have the same question like I wouldn't. So I guess you've done that.
Oh yeah, absolutely. We would be doing it here, but we don't have the scale. There's no reason. I'm going to show you a picture. I wish I don't know if you've heard this. They're talking about going online with a lot of courses here. Are you guys in on that? You've heard, some of you heard that, right? Including the labs. I don't know how you have a lab online personally. However, one of the reasons why I'm getting into starting to maybe film a few things and stuff like that is that I think one of the ways that maybe to supplement, because we don't really have a lot of equipment that would be nice to do, is that I can sneak into some labs occasionally and actually can fill these and so on. Now, let me ask you something. How do you think these things get filled? You think there's like a machine somewhere or God fills them or something like that? There's a guy like you sits there all day long and fills it, weighs them and fills them.
So if you're getting them from a lab and you're sending them to a lab, I'm not the lab, and I'm supposed to be collecting the sample. I mean, that's just the little that I thought. I wouldn't want to contaminate it or.
Well, you would have to do it in the clean area, but there's also keep in mind now that whenever you do this, you also do blanks, right? So in other words, you will be control. Well, you make your own blanks too. You can make your own blanks as well, right? So I mean, there may be times when you have to do this yourself, or God forbid, you might actually get a job in a lab. The only difference between you doing it here, the only difference between you doing it in this room and doing it in a laboratory is the laboratory is a better controlled environment. Now they're not going to be doing this in a clean room. They're going to be doing this in an ordinary lab, maybe in a hood or something like that, but not a clean room. So I mean, the environment, this room, if this room had a hard floor instead of carpeting, I would say almost undoubtedly that the dust level in this room would be the same as it would be in the lab that you build these things in, or the lab that they work on these. Yes.
Well, the other is having a lab
I guess you can make that argument that it's like a third party that actually does the measurement of the cassettes, but and then you're just doing exposing them and so on and so forth. Yeah, but it's good to know how to do this anyway. No. Okay, so you're gonna take this apart. You're gonna get a new filter. You're gonna simulate weighing it. You're gonna assemble it, put it back together, and you're gonna put together your sample train. When you got your sample train together, bring it up to me so I can look at it, make sure it's all put together correctly. This cassette. Now, let me ask you something. Let me ask you something. Now, this cassette actually has three parts. This cassette actually has three parts. This one's only two parts. I can't take the other part apart. Oh no, wait a second. Yeah. Yes, I can. This has three parts. I didn't bother cutting open the top part of this thing, only the part where the bottom part where the filter is. The third part can be taken off also. So this cassette, well, essentially the filter will be sitting in here. It'll still be held in by the second part. The filter will be sitting in here like this. That's an open face sample, right? Most particulates that you're taking, if you're taking gravimetric readings, most of the time you will not do it open face. You'll do it with the old cassette, all three parts of the cassette together, and you just simply pull out the plug. Okay, and the reason for that is it makes it less likely you're going to get some sort of cross-contamination with some other big particles or something like that landing on the filter. This will be facing downwards, so you won't get stuff dropping onto it, so on and so forth. Okay, so you would do it typically closed face, just pull a little plug out of it. Okay, so why can we do it that way? Because it doesn't matter where on the cassette that the dust settles, that the dust is captured, where on the filter the dust is captured, because we're going to weigh it. So it doesn't matter if it's mostly in the middle or on the outside and so on and so forth. Anybody know what this cassette is used for? This is a 25 millimeter cassette. Asbestos, this is used for asbestos. This, you use open face, right? Now, why is it so long and narrow? Why do you think that might be? Want to hazard a guess? You want to get a nice laminar flow because unlike measuring the weight that we're doing with gravimetric analysis for nuisance dust, with asbestos, we're going to count fibers, right? So fibers are so tiny that there could be tens or hundreds of thousands of fibers on this filter when we're done, right? So there's no way in the world you're going to count every fiber. You're going to, under a microscope, select small areas and count them and then use that as an average for the whole filter, right? You're randomly going to select areas. So you need a nice laminar flow that evenly deposits fibers over the entire cassette. So when you're doing filters, you want a long cassette so you get nice laminar flow, you get an even distribution of particles on the filters. So when you look at that filter, you can randomly pick areas and do your fiber counts. It's important you get an even distribution of filters so you can count them correctly. This one, gravimetric, it doesn't matter because you're just interested in the weight. It doesn't matter if it's all stuck in the middle because that's where that hole was, or if they're all distributed throughout the filter.
I'm curious about the asbestos one. I haven't seen them. So they'll put a cassette on the end of them and just collect it in there. That's the cassette.
Well, there's a filter at the back of this. It's just like this one. There's a filter on the back of this to collect. It's a different filter material, but there's a small filter on the back of this, just like there is on here, except that there are going to be fibers on there. In fact, I'm going to toss this back there. So you guys can. There you go.
There's two different kinds of ways to do it. Depending on the analysis, two different types.
Yeah, we're going to be talking about asbestos. I think we're going to be talking a bit about asbestos next week and VOCs next week. We're going to use other kinds of devices since we're going to use devices that are specific to the kind of material that we want to capture. Okay, so I never see anybody use what other kind of cassettes do you see them use?
What is the PCM and PCM?
Oh, okay, I got you. All right, okay. Okay, so I only see them used for PCM, but that's okay, doesn't matter. Okay, so here's our sampling train. Here's what, can you see that? Here's our sampling train. There's our cassette up connected to its collar. Now, you don't need to have this, but it's nice to have a device to hold this securely in the worker's breathing zone. So in order to do that, we have a device like this, a little holder like this. I'm going to mount this and toss it down. I'll get your filter back to you later. Okay, hang on a second here. Oh, I got to put it this way. Okay. Okay, there you go. The bottom, the blue tab, right? The inlet is on the bottom. Okay, there's a little tube coming up here, and there's a connector for the tubing that's going to go to your pump. This is cut off, but it would normally go to the tubing. We can actually take this off, cut this off, and actually connect it to our pumps as we're working. So this can go into its breathing zone. It's facing downward, so you're not going to have a lot of junk, and it's closed face, so you're not going to have a lot of junk getting into its getting into the filter. That might just be falling out of the air, and so on and so forth. So you get a representative sample of the actual dust in the air, and it's close enough to its breathing zone to be able to measure it. So this is then going to go to our pump. Now, so the problem now is that this is going to resist airflow. So when we run our pump, if we connect this directly to the pump, right? If we calibrate the pump and it's pulling 1 liter per minute, and then we connect this filter to the pump, it may not be 1 liter per minute anymore, right? So we need to calibrate this pump with a cassette in line. You're not going to use you're going to use the same type of cassette, a clean, new, same type of cassette as you're going to use for the filter, but you're not going to use the same one as you're going to take your sample with. So you're going to take a cassette, same kind of cassette, you're going to connect it, you're going to connect the calibration device in between you're going to connect your calibration device to your inlet here. You're going to go through the filter and then to the pump. So now when you measure your calibration device, you'll actually know how much air is actually being drawn through this filter. Okay, so if this was 1 liter per minute without the cassette on, now it might be 0.9 liters per minute. So you're going to want to take 3 readings, 1 reading, 2 readings, 3 readings, average them, and that's going to be your pre-sampling flow rate for your pump. Then the worker, you're going to disconnect this device, and now you're going to put in your actual sampling cassette. The worker's going to work with it for 4 hours, let's say, in a dusty environment. He's going to come back to you. You're going to retrieve the cassette. You're going to then take the cassette apart. Well, before you take the cassette apart, you're going to put your calibration cassette back in. You're going to measure the flow again to see if the pump rate has changed. So now if the pump rate is lower, if it's the same, that's great. If the pump rate is lower, now you take 3 readings. You take the average and you say, well, before I started, it was 1 liter per minute. After I finished, it was down to 0.8 liters per minute. So I'm going to assume that the average flow rate over those 4 hours was 0.9 liters per minute, an average of the before and the after. Okay, you take 3 readings because you want to make sure you don't get a bad reading by just taking one. You want to make sure you get a decent estimate of the pre-sampling velocity. 3 at the end, and then you're going to average the 2 of them and use that as your flow rate. Okay, and on your charts, and I'll put those up here. Yes.
You're saying that after the reading, you put in the calibrated part filter in there to see if the
Yeah.
Had dropped.
Yeah, in other words, you're going to have one of these that you're going to put aside and you're going to use it for your calibration. If I use this to measure the worker's environment, I'm not going to connect it to my calibration device and use it for my post-flow reading. I'm going to replace it
Use the ordinary
with an ordinary cassette. Yeah, it's not going to be exactly the same, but you don't want to expose this to. Yes. You know, I think that in the NIOSH standard, I think they actually mentioned that if the difference is more than a certain amount, more than 25% difference or something like that, then the sample may not be valid. But that would be a relatively rare event, right? That shouldn't happen. Unless there's a problem with the pump, that shouldn't happen. The other thing that could happen to cause that is the filter could get so packed with dirt, with debris and dirt, that it could change the flow rate. Right? That's conceivable, right? But in order to avoid that, the NIOSH procedure actually has a maximum flow rate and number of minutes, assuming that you're at the PEL, that the dust level is at the PEL. You can't run for more than a certain number of minutes at a certain flow rate to avoid clogging up the filter. Okay, so that's the way they avoid that being an issue. Okay, pass this around. Okay, so everybody can get a look at that. Okay, so now, how are we going to deal? What if we only want a respirable sample?
Before we move on to
Yes.
another question. So you're saying that, okay, first I calibrate it,
Yes,
put it aside, put the new one in, right? And then take it out, put another one in, calibrate.
Correct.
So let's say the first average was 1.
right.
And the second time I calibrate it again, I come up with, let's say 1.5. So
Well, it's going to be lower. No, almost, it's not going to be high. Yeah.
So you come up with 175. So what
Yeah.
do I do?
Right. You take the average of those two, and
Just
that's
two.
the average read. That's the average flow rate during the entire period that it was exposed. Okay. Okay. So now we got another headache, and that is, what if we don't want total particulates? We only want respirable particulates. Well, now we need some sort of device that's going to separate particles into sizes that we want to capture and particles that we don't want to capture. The simplest of those devices is called a cyclone. In our garbage can here, I need to get something better to work with this. I'm going to screw this on here so I can get it. Okay. I thought I had an aluminum cyclone, but I guess I don't see one. This is a simple cyclone type device. The aluminum one that you see there is a bit more common. And what this does is, this is connected to your cassette. This is connected to your cassette. You're pulling air in through this little tube, this little hole that's on the side of this thing. And air is then going through your filter cassette and then back to your pump, right? So this goes in the line of flow before your cassette. Okay, what this does is that air is coming in here and air is spinning quickly in this device, just as it does with that aluminum one that you see behind me, the one that's all the way over on the left-hand side there. You can kind of see on the right-hand side, you see that diagram of what's going on in there with the airflow. These are designed so that our particles over a certain size are captured and fall out into this little collection device at the bottom here, this little plug at the bottom. Okay, so particles bigger than 10 microns will be captured and fall out here. Particles that are smaller than 10 microns will continue along and be captured by your filter. This is called a cyclone. Okay. This device, there's a million of them. You see this little plastic one, you see that aluminum one, you see this other plastic one. There's a million different forms of these things. The important thing about these is that they're made for specific separation, size separation. Might be for 4 micron, might be for 10 micron, and for a specific flow rate. So let's say, for instance, that this one is designed to remove particles larger than 10 microns. So you only get the particles that are respirable smaller than 10 microns. This device has to operate at a certain flow rate. In other words, you can't run it at 1 liter per minute. If it's designed for 1.5 liters per minute, in order to get that particle separation, it's got to run at 1.5 liters per minute. Can't run at 1, can't run at 2. So even though the NIOSH procedure says that you can run in this range, in order to make this valid, you have to run at the specific flow rate that it's designed for that particle size separation. I'll see if I can come up with a couple of others of these.
What if the pump is losing pressure, losing power? So how do you?
Yeah, again, we're going to accommodate for that by calibrating before and after we're done. You know, we're going to do two calibrations. We're going to calibrate before and after. Now, there's a problem with calibrating this, right? Because now we don't have a tube to connect it to our calibration device. Well, in fact, the manufacturers provide a calibration tool for this where you can connect this to a calibration device. So since you don't have a tube to connect, you don't have a tube at the bottom to connect it to. It's going into a little slot on the side. There's either a thing that slides over it or a thing that slides around it that allows you to calibrate it with this in the sample train. Okay, so we're not going to worry about that though. We're going to just do total particulates, unless I can find some others. Now, there's much more sophisticated versions of these. I'll talk about this at the very end. This is a personal modular impactor. This is the device that actually uses the sample stream comes in through four holes in the front of this device. There is an oil filter surface, there's an oil pad that goes over the inside of this, and it actually, larger particles, as they're pulled into here, they impact that oily surface. They get captured on that oily surface. Smaller particles manage to make the turn go around and manage to reach a filter that's in the back part of this cassette. Okay, this is a bit more modern version of how people would take these samples. But to tell you the truth, I think the cassettes are probably pretty standard for most analysis. These are expensive, so you don't see as many people using them, right? But if you do a lot of sampling, they're worthwhile. These have an advantage in that they're more efficient at removing the larger particles because that oily surface tends to really capture the particle. Sometimes when you have a hard surface, it'll or in that cyclone, they'll bounce around and they'll manage to get around and get onto your filter as well. Because this has less of that bounce effect, where a particle that's larger than you want can actually wind up on your filter. So these are a little bit more efficient than the more typical ones that we see, the SKC filters that you see there. What's that? You know, I think there is, and I think it might. Yeah, I'm pretty sure that there is, because it's similar. It depends on the mechanics, the physics of the particle size, the momentum that the particle has in order to impact the surface and capture. So yeah, there's always got to be a flow rate that these are intended for. You know, the NIOSH method probably doesn't describe these. We're going to look at the NIOSH method. It probably describes the SKC cassettes, right? Probably doesn't describe this. You don't have to use, for ocean, you don't have to use the NIOSH method. You have to use a method that is valid within a certain range of accuracy and a certain standard deviation of results, right? There's a range, like 95% accurate and within a certain number of standard deviations for the results from the actual value, right? So you don't actually have to use this. You have to use a method that you can defend that will be equivalent to this. So even though this may not be specifically named in the NIOSH method, doesn't mean you can't use it. In fact, it's actually probably more accurate than the NIOSH measurement. Okay, so particle size. Okay, so what about our calculations? At the end of the day, we're going to wind up with two main numbers that we're concerned with. The weight gain in our filter, right? So that's going to be the weight before, the weight after minus the weight before. Simple enough, right? Over the flow rate times the amount of time. The flow rate times the amount of time is the volume of air that you sample. If you're sampling at 1 liter per minute for 2 hours, you've sampled 120 liters of air. So we want to get the concentration in milligrams per cubic meter, right? So the flow rate, if it's in liters per minute, times say 120 minutes, you have 120 liters. And the weight gain, if happens to be in milligrams that your weight gain is measured, right? If your weight gain is in milligrams, well then you can multiply by 1,000 to convert from liters to cubic meters, or divide by 1,000, convert from liters to cubic meters. We'll work on that. We'll work out those numbers once we get to that point. Now the weight gain, though, let's think. If the flow rate seems pretty straightforward, you're going to use the average flow rate, the average of before and after, times the amount of time that you sample. Pretty straightforward. Well, what about the weight gain? There are things that could happen that would compromise your estimate of what the actual weight gain is. For instance, you're assembling these you mentioned before, it's not a lab. You're assembling these in a dusty environment. You're putting together your sampling train in a dusty environment, and so on and so forth. Maybe there's something in the air, some other kind of aerosol that winds up getting on the filter before you get started in the environment where you're putting together your sampling train and so on. Okay, so that's going to affect any sample you assemble in that environment. Okay? Any sample train you assemble in that environment. So what do? You do a blank. You take a cassette, you assemble, you work with it, you open it, close it, work with it exactly the same way you would work with your sample cassette. And then at the end of it, you reweigh it again. Most of the time, the weight before and the weight after is going to be the same. If the weight after is greater than the weight before, there must have been something in the environment that you were working in that caused that weight gain that was not part of your sampling period. So what you do then is you take your weight gain, on your filter, and subtract the weight difference in your blank. So if your weight gain was 150 micrograms, but your blank increased 2 micrograms, right? That what you would do is subtract those 2 micrograms from the 150 micrograms in your weight gain, because whatever happened to your blank probably also happened to affect your sample as well, since you handled it exactly the same way. Okay, that's the only complicating factor here. And when we finally get down to this and put this together before we finish up tonight, we'll go through this entire thing and we'll talk about how to complete that. There's a spreadsheet also you can use to finish that up as well. Here's the kind of balance that you would be using when we do a gravimetric or a mass analysis. Right? So this device is accurate down to a microgram, a thousandth of a milligram. We'd actually take the filter, put it onto that device, weigh it, take it off, put it into the cassette, and then after we're done, reweigh it on the same device. Here's a typical. This in particular is for calibrating the flow rate. They use a rotometer, right? Not the best thing in the world. Here's a more accurate way of measuring the flow rate. In this case, they actually have a cup goes over the cassette holder. Okay, we'll go over the numbers later on. Okay, all right, so I think this might be a good time to actually give this a shot. Okay, so pocket knife, and I think I can come up with another one somewhere. And so work in teams, open up the cassettes. Here are your filters. Here are your backings. Here is a ton of tubing, and you have your cassettes already. Open them up, remove what's in them, assemble a new filter and backing into your cassette. Put it together and turn on a pump. I don't know how many of these are working. Don't worry about the flow rate on those pumps. I'm going to put up right now. I'm going to put up the NIOSH procedure. 2 or 3. Well, we're not. You're only going to run the pumps long enough to calibrate. Okay, we're not going to really take a sample. Okay, guys, here is the NIOSH procedure for particulates not otherwise regulated. The flow rate, the sampling device has to be a tared, weighed 37 millimeter 5 micron PVC filter. We've got those. Flow rate is 1 to 2 liters per minute. The minimum volume for determining whether or not you exceed the PEL is 7 liters. The maximum volume is 133 liters at 15 milligrams per cubic meter at the PEL. Why is that? Well, it's got to be at least 7 liters to accurately, using this method, determine whether it's above or below 15. And you don't want to go over 133 liters if there's that much dust in the air, because it'll clog up the filter. Okay, and once you're done, the measurements are done using a balance that is good to 1,000th of a milligram sensitivity, with a range of 0.1 to 2 milligrams per sample, and so on and so forth. And there's more details about the procedure that follow there. Okay, so for starters, if you look at this, let me open up that sheet too. Okay, so what are you going to put on there? Date and location, as if you're doing an actual sample. Technician, the initials of the people that are doing it. Pump, model, make, and serial number. The media type. The sample media ID number. In other words, if there's a ID number on that cassette, you can put that on there, or you can make up your own ID number. Okay, because you're going to give this to a lab, so you're going to want to label these things so they can identify which sample they are. You want to identify what contaminant that you're going to be looking for. In this case, it's nuisance dust. You want to tell me what particle size that you're sampling. Okay, is it total particulate, or are you using a cyclone to measure 10 micron and smaller, or respirable dust 4 microns and smaller? You want to tell me what NIOSH procedure that you're using. Happens to be 0,500, and then you're going to put in the filter weight before and after, and the blank weight before and after. I will give you those. Okay, I will post on Blackboard sample weights for it. If you send it to the lab, I'll give you those sample weights after you're done. Okay, and the weight increase attributable to the particulate is going to be the difference between the sample weight gained from the filter and from the blank. And then you're going to calculate how much air that you actually sampled. Pre-sampling flow rate, which is the average flow rate before you started sampling. Post-sampling flow rate is going to be average flow rate after you're done sampling. So you're going to do 3 samples, run the pump for a little while, do 3 more samples as if it's after you're done. Okay, and you're going to average those 2 sets of 3 readings, and you're going to give an average flow rate. That's going to be your liters per minute. You're going to base your exposure time on. You're going to give a start time, a stop time, and a duration. I'm going to tell you right now that the start time was 9 a.m. and the stop time was 11 a.m. So you sampled for 3 hours, 180 minutes. Okay, and I'll give you weights on Blackboard. We'll make believe that you send these samples. You see, well, this is all information you would have, right? The flows you would have, the weights you would not have until you got the results back from the lab or from whoever was weighing them for you.
9 to 11 is 2 hours.
9 to 11 is to your right. Let's make it noon. Okay, so start assembling.